Okay, Tomasz, you're being recorded, so go ahead, full steam.
So after these two beautiful and very detailed presentations, my presentation of the third work package will be more succinct and more philosophical.
Sorry, Tomasz,
Yes?
I'm not sure you realize, but we can see you up to your nose. So we can look up your nose, but we don't see your eyes, which is a little bit. I prefer to look into your eyes than into your nose.
I cannot see even my
Just tilt the screen a little bit because somehow.
I don't know how to do this.
Okay.
Is it better?
Now it's better. Yes. Yes.
Okay. Okay. So, as I started, I will be talking about the third work package, the graphs and groupoids, and maybe I will say some words how this work package could be related to some other work packages. So the motivation for the work package consists of several observations. So first of all, it is well known that many sister algebras are stably isomorphic to groupoid sister algebras. Such graph groupoid sister algebras form an important class of sister algebras which are defined by means of combinatorial data, thanks to the results of Kumjian, Pask, and Rayburn and Renault. And from the very beginning of the program of Renault of modeling sister algebras by groupoids, the two questions are the most important ones. First, it's about the relation between the combinatorial or topological structure of this groupoid model and some invariants of the sister algebra, for instance, K-theory or some other invariants. Besides this prominent question, one could try to find for these models the most convenient presentation, because usually groupoids are structures which are as complicated as spaces, as homotopy types. These are too general to be treated from the scratch. Usually, for instance, in homotopy theory, people deal with some presentations chosen in such a way that some invariants, some properties could be easily computed or checked, and usually it makes this theory computable. For instance, if your model or your presentation is of combinatorial nature. Today, we are at the situation where when the question about linking graph properties and properties of sister algebras could be related by groupoids. So this is the main idea of this package. So first of all, let's start speaking about groupoids. This idea about groupoids, which can be used as models of sister algebras, is not the usual idea coming from category theory or algebraic topology. It was introduced by Stanisław Zakrzewski, who essentially observed the following phenomenon: that the groupoid is a partial structure, in opposite, for instance, to the algebra or a group, when the multiplication or composition are defined totally. composition in the groupoid is defined only partially. Okay, so this makes the theory of groupoids more complicated, especially if you want to speak about representations of groupoids, because arrows in a groupoid are not parameterized by a single parameter, but every arrow has its source and target, and the composition puts some conditions on these arrows of composability, which makes the representation theory of groupoids more complicated. However, there is some way to bypass this difficulty, thanks to Zakrzewski, who observed that the groupoid could be regarded as a group object, which means it's something with totally defined structure. However, in the symmetric monoidal category, not of sets with mappings between them, but symmetric monoidal category of sets as objects, but with relations as morphisms.
Mm-hmm.
Okay? And then he created a functor from groupoids related by Zakrzewski relations to sister algebras, which could be regarded, which is contravariant, but which can be regarded as a covariant functor from groupoids with relations as morphisms to, let's say, non-commutative spaces.
Well, wait, covariant or contravariant? Because you have an O here.
To sister algebras, it is contravariant. If you want to think about sister algebras as non-commutative spaces, reversing arrows in this category.
Okay, I've got you.
Makes it a covariant functor.
Yeah, thank you. Yeah.
Okay. So as Piotr already mentioned, the structure of a graph, for instance, sometimes is very or resembles very much the structure of a space which is built with some pieces. So these gluing spaces in the category of topological spaces is known under the name of pushouts. Also in the category of groupoids with Zakrzewski relations, one could speak about pushouts. And then the first question could be asked here in this in the context of the covariant Zakrzewski functor from groupoids to non-commutative spaces is whether this functor preserves pushouts or gives, as Piotr call it, theorems of type from pushouts to pullbacks. This idea is somehow related to the topic of the first work package, because for every graph we can construct a category of one-sided infinite paths, or you can take triples consisting of paths and pairs of paths and integers, and you cook up with the structure of a groupoid, which can be given a topology which is locally compact, sigma compact, totally disconnected, and Hausdorff. And the corresponding sister algebra of this groupoid is nothing else but the Kunz-Krieger graph sister algebra. So the natural idea is to restrict these Zakrzewski relations to the category of groupoids coming from graphs, and then it would define some kind of relations between graphs. Okay, but this gives some benefit from this passage, because then we start from, first of all, some structure of the category of equivalence classes of graphs with some morphisms, and we have a functor, which is a categorifications of the Kunst-Krieger graph system algebra.
And you really mean here Kunst-Krieger? So these are not general graph system algebras, just Kunst-Krieger.
Even general graph system algebras.
Okay.
So this is the relation with first work package, but in this groupoids could encode, for instance, some symmetries, some actions, some, for instance, more complicated transformations coming, for instance, from equivalence relations between combinatorial data, similar, for instance, to Penrose tilings, which couldn't be treated by means of symmetries in the usual sense. I hope that this approach could shed some light on problems about sister algebras having combinatorial presentation in general. Okay, so one of kind of extensions of this idea of treating relations comes when we try to first linearize and then non-commutative relations to obtain sister correspondences. So this
quantize.
Sorry?
Quantize.
Instead of non-commutative, you can say quantize. Yes.
Yes. So quantize is about making everything linear, and next being representations of sister algebras. So quantized in short. Okay, and then you obtain sister correspondences. This is a theory which is developed by mostly Meyer and collaborators. Ralph Meyer with collaborators, and embraces such important cases of sister algebras like cross products, Kunst-Pimsner algebras, topological graph sister algebras, groupoid sister algebras, and some even more exotic constructions like actions of OR monoids on spaces by topological correspondences. Okay. And it turns out that in this approach, properties of the underlying groupoid are related to properties of the sister algebra. For instance, the ideal structure or the properties like pure infiniteness of the sister algebra. These can be rephrased in terms of this C correspondence structure. The most important correspondences are Morita equivalences. And in this case, there's a lot of very precise, very concrete and satisfactory results due to work of Abrams, Tomford, and Eilers, Storff, Ruiz, and Sorensen. So first of all, Morita equivalences can be seen on the level of the graph, and they can be seen by sequences of some transformations of these reconstructions of these graphs, which are called graph moves. And this descends to a very analogous concept at the level of the groupoids. There is a problem in this approach because it is not very clear how invariance and some properties of sister algebras can be related to some properties or invariance of these groupoids themselves. Okay.
Just a silly question: are these the same moves that Soren was talking about?
Yes. So I'm referring to these papers by Iles, Restores, Uris, and Soren.
Oh yes, of course, yes.
However, if you want to compare the structure of the groupoid and invariance of the arising sister algebra, the situation is not clear, and we have some examples and counterexamples. So this means that this theory is very far from being satisfactory. There is some other approach in a much broader context of sister algebras, which are defined by combinatorial data. The most prominent example in this class is something that's called temporally Lieb algebra. Okay, and this temporally Lieb algebra, although it has very simple presentation, it's even simpler than the Kunz-Kluger relations. It founded very deep and very important applications in many branches of mathematics, from statistical mechanics through integrable models, graph theory, knot theory, the braid group actions and representations of the braid group, quantum groups, and classification of subfactors for Neumann algebras. Everywhere, the role of temporally algebra and their representations, and even more importantly, invariants, which are cooked up by means of these representations. The role of this relations with this invariance allowed people to solve very important problems, very big part of mathematics. For the temporally Lieb algebra, the most important invariant, which is different from previously presented, for instance, K-theory, even if K-theory is enhanced by some additional structures, is the Jones polynomial, which translates the combinatorial structure of the model, combinatorial model, inducing the sister algebra, or from Neumann algebra, go and transforms it to pure algebra. Okay, so in this work package, objectives are fourfold. So first of all, the first aim is to establish links between graph properties and sister algebra properties by applying ideas of sister algebras, of groupoids related to graphs. The second task is to find topological and geometrical properties of groupoids, which could be applied to study the corresponding sister algebras from the point of view of other conjectures in mathematics related to, for instance, to questions of symmetries or representation theory, like Baum-Kohn conjecture and Matui-HK conjecture. The third is about extending the results obtained by Meyer with collaborators about actions of Ore monoids on a tall groupoid. So groupoids is already something encoding some kind of dynamical system. But this dynamical system can have some secondary symmetry. And this secondary symmetry is encoded by the action of, for instance, some monoid. And when this monoid satisfies some algebraic property, which is called the Ore condition, then there are some results in this direction. Okay. And the last is a very long shot because the project is about trying to extend the Jones polynomial or some invariant of similar fashion to a wider class of combinatorial structures like graphs, diagrams, categories, groupoids, etc. Okay. Methods which can be used to achieve these aims are different. Some problems, for instance, in the first two tasks, I expected that they could be only case-by-case studies. The third objective could be obtained by utilizing methods which were worked out when people were talking about sister algebraic properties of sister algebras of such models, combinatorial models, or some group or groupoid models like self-similar groups by Nekrashevich, self-similar graphs like Excel and Pardo, self-similar K-graphs like Huili and Dilian-Yang, irreversible algebraic dynamical systems after Stammeier. And in the last objective, of course, the methods come from the well-established properties of the function of K-theory, which is computable for graph sister algebras, thanks to Rayburn, Szymanski, and Drennan Tomford. And there are some other methods worked out in the case of quantum groups, integrable systems, and topology. So combining all these things, it's quite possible that some kind of some generalization of algebraic invariant of combinatorial model like Jones polynomial could be conducted. So this is everything I prepared. If you have a question.
Okay, so let's fire at will if you have any questions.
Of course, I cited experts in the fields, which I listed, but if you want to ask me some question, I could try to answer at least.
Because somehow, Tomasz, you have 20 minutes left, so.
Yeah, so this plenty of time for questions.
Okay, Soren, go ahead.
So maybe this is more of a comment for this thing about moves. So first of all, I mean, we have these moves that they sort of have a hierarchy of niceness, right? So the outfitting is very nice. But the Kunstsplice is not nice. That will not preserve the groupoid. And actually, I mean, this is something that we thought quite a lot about in our project. If the nice moves will generate groupoid isomorphism, for instance. And we know this in some cases, but not always. So there is work to do there. I mean, it's true that that's probably the way that you're using it, right? I mean, these moves are invariant, but we don't have a sort of complete classification saying that if the groupoids are the same, then you can go from one to the other using only these invariant moves. This we know in the classical, in the Kunstkrieger case, but not always. So this is an interesting project that we might as well. So,
if I understand well, do you stress the role of the secondary symmetries?
I'm sorry?
Do you stress the role of the secondary symmetry? Different from this groupoid model?
I mean, so the thing is that for the groupoids are isomorphic if the C-star algebras are isomorphic in a diagonal preserving way.
Mm-hmm.
And so and those moves that we have that are diagonal preserving, these are the outsplitting and the insplitting and the reduction and the source addition. And in some cases, I know that the groupoids are isomorphic. The graph groupoids are isomorphic if and only if I can go from one graph to the other using only diagonal preserving moves. But if I have infinite emitters, for instance, I know absolutely nothing. And we thought about this. I mean, we worked pretty hard, but we couldn't get through. So this may be something. I mean, if this is useful for something, we might have another go at it. So.
Yeah, it was only the project. If of course on the way of obtaining some results, of course, collaboration is expected and
yeah.
Very
and also, I
welcome.
mean, it's okay. I mean, you can take these moves and you can change your graph, and this will give you a groupoid isomorphism. This we know. But the question is it sort of if and only if?
Yeah.
I know sometimes, but not always. I think this would, I mean, if you have use for this, that I would be very interested in learning about.
Of course, I didn't know this. So this is even beyond Morita equivalence, and this relation with this diagonal subalgebra. Something new to me. So is it published?
There is a Efren Ruiz and I have a paper on the archive, which is a couple of years old. We're trying to make a new, better version of it, but this is the so-called, I mean, it's a terrible notation. We call it XYZ isomorphism. So we have these different kinds of isomorphisms, where X says, is it on the nose or stately? Y says, does it preserve the gauge action like the equivariant? And Z says, does it preserve the diagonal? And what we're talking about here would be like a 0-0-1 type of isomorphism. That's a stabilized isomorphism that sends the stabilized diagonal to the stabilized diagonal. And this translates, and this is general for unital graph algebras, to the graph groupoids being stable. You sort of stabilize them in a similar way with this thing R. This is a result of previous, not me, but yeah, I'm a little bit unsure what the right reference is, but this is known to be if and only if. So we have things of this nature, and then we try to prove, and we sort of fail to prove that if you have an isomorphism between the graphs that sends a diagonal to the diagonal, then you can go from the one graph to the other using only the moves that are nice, right? So you're not kunstsplicing. I mean, so we know we can go from one to the other just because the C-star algebras are isomorphic, but now we know more and we want to say something more precise. And this we know in some cases, but not always. We know a little bit more that's on this than what's on this archive.
So, do you think that this part of the project is too ambitious?
No. I just want to point out that I think it's true. I mean, I think it's true. I think it is an if and only if between them. I mean, it's a complete connection between the diagonal preserving isomorphisms and the nice loops, but I just have to admit that I cannot prove it. That's what I wanted to point out. But I think it's going to be true. We're just not there yet. Thank you.
Yeah, I see. Thank you very much for this comment.
Okay, Ralph.
My question actually is to you, Piotr, and maybe to Tomasz, both of you. It's about these new morphisms that you spoke about.
Yes.
In a graph C-star algebra, you have the diagonal. This commutative subalgebra functions on the objects in the groupoid model for it. And do your morphisms always preserve this diagonal? Have you thought about this?
No, it is not.
They don't. Okay, this is because
No, we don't. This is are not mapped in the same way as arrows. At least in the Zakrzewski approach.
They are different. You know this.
They are different. Yeah. These are not functors. These are not things that are related to algebra. Yeah.
Of course, I know that. I think that these Zakrzewski-like morphisms would preserve the diagonal inside the groupoid C-star algebra automatically, wouldn't they? I think that should be a property of them, although I haven't thought about it much. I would have to look it up.
Zakrzewski relation or morphism must be compatible with units. But does it mean that it preserves the unit? What does it mean?
I mean, this in the C-star algebra, it induces a star homomorphism between the C-star algebras of
diagonal
the groupoids.
subalgebras.
And then there is a diagonal subalgebra, and I would think that these Zakrzewski-like morphisms contain a map between objects in the opposite direction. And I would guess that on the diagonals, you just get the star homomorphism induced by this continuous map. Well, I would have to check this more carefully. It's just kind of an obvious guess that it should be so.
I'm not sure. Maybe.
And I think my doctoral student, Jono Taylor, should know this better, but I'm not sure he's still around. Is he still here?
Yep, I'm here. My understanding, if these are the same Zakrzewski morphisms as what Bunecci and Stakura studied, then yes, these the star homomorphism you get on restricts to will preserve the subalgebra because it just comes from the pullback of a continuous map.
That's what I was thinking. And then to compare these morphisms to the new morphisms that Piotr spoke about, the first question would be whether those also preserve the diagonal. If they do, well, then I think what Jonathan is doing, what you are doing right now, should probably give you a few more conditions to check that would imply that they have to come from a Zakrzewski-like morphism. So that should be pretty checkable, but I was wondering whether you have checked this already, Piotr, or
no, I have not. But let me tell you, make the following remark. We should really distinguish these two different types, the covariant and contravariant. So in the contravariant case, basically, so first, every star homomorphism that is induced is equivariant under the gauge action. Okay. So that's this feature which we definitely do not have in the covariant case. And here, our way of moving behind of what was known earlier was simply allowing a little bit of non-injectivity. So that's the only thing that was changed from what there used to be before. So maybe if you just ask your question, because it's been well known what it means that you have an admissible subgraph. Well, we just called it admissible subgraph, but basically these are all these properties which are very well known of how you go to the subgraph, and then you have a quotient and how you produce ideals. These are textbook stuff. So if these type of morphisms preserve the diagonal, so that would be my question to you. If in the contravariant case. Now in the covariant case, we no longer preserve the length of a path is no longer preserved by the morphism. So we completely lose.
That's fine. That's not a problem because the diagonal subalgebra would be more like take projections given by all the paths. So take all the, for any path, you can take the range projection or the source projection inside the C-star algebra, and all these projections would commute. And that should be the diagonal, I think.
Yes, commutativity, this is covariant, commutativity should be preserved. I see. Don't see why not.
Since you haven't thought about it, I suppose Jonathan might think about this as an further application of these morphisms of Cartan inclusions or slightly more general. So just check whether these, which morphisms of graphs of which different kinds would preserve this diagonal and have the other properties that you want. And then, since you haven't thought about it, probably he should do it.
Okay. Well, that's exactly for proposing first steps for research. So that's perfect. Okay. Any further suggestions or questions? Yes, go ahead. I see. Oh, this is a thumb up. Oh, so Jonathan, this is a thumb up or a question?
This is a thumbs up to say I'll look into that. Yeah.
Perfect. That's the spirit. So I suggest maybe that in the remaining 9 minutes, because I suppose not everybody is so well familiar with the Zakrzewski relation. Tomek, would you mind recalling of what this mysterious Zakrzewski relation is? Because it's kind of absolutely pivotal to what you are talking about.
Yes, so let me. I cannot. So let me start. I'm looking for.
Yeah, just share the whiteboard and then use it.
Yes, I'm trying to find this. Something happened in my Zoom. Oh, yes, it's here, of course.
Great, we see the whiteboard.
Okay, so if you have, why I cannot write on this? Okay, if we have gamma, a set, then we can speak about relations between. So I will denote the relation by an arrow with a solid arrowhead. Okay, a triangle arrowhead, and we have composition, which is a relation. Relation, first of all, is a subset of.
I'm not sure you realize, but somehow your screen, we see only part of your screen. So most of your writing is outside of our screen.
Oh, it's strange. You don't see my full.
No. I mean, your letters are gigantic.
Are you talking about the screen or whiteboard?
Whiteboard.
I don't know why.
Maybe. I mean, you're writing behind our field of vision.
Okay, so please tell me where is the
on a screen, you can make
limit of the visibility of my writing. Is it here? Can you see this line?
Well, I will draw. Oops, I cannot. This is strange, but I have no. Can you stop sharing and start again, because there's something wrong with the way,
please.
because
Yes,
normally I should be able to write on your screen.
again,
Yes, whiteboard, just regular whiteboard.
yes.
Okay, and I should be, yeah, no,
Can you see it?
yeah, I can see it, but I cannot write on it, which is weird. And Ludwig can write
It's
on
a
it,
matter of
okay.
your annotate.
Yes, I can write, and also there is on the right, the lower corner, there is scale. You can reduce the image from 100%.
Okay, yes, okay, I see it. Okay, fine, fine. Okay, Tomasz, go
Should I
ahead.
reduce it?
Right now, we didn't write anything, so I don't know.
Ludwig is writing.
Yes,
Well, I reduced my screen, my whiteboard. I don't know if Tomek can do this the same. I don't
Yes,
know.
I did the same. I reduced to 67%.
Okay,
yeah,
so
we can
I
do,
do
yeah,
right.
that's a new feature. I wasn't aware of it. I mean, it's completely new.
Okay.
So Zoom is evolving. Oh my goodness.
Okay, so you probably know what are relations. So two argument relations on a set X is a subset of the Cartesian square. Okay,
Yes.
and you know that these, even for relations, where is this? I cannot find the operation of undoing. No, I cannot see it. I have to use this. Okay, if you have a relation, a subset of a Cartesian product, okay? Why I'm calling it R? I should call it F. Okay? Maybe capital F, whatever.
Whatever.
And I have subset of Y cross V. Okay. Then the composition of these is a subset consisting of such pairs, if I remember well, X, Z, such that there exists Y, such that XY belongs to F, and YZ belongs to G.
Yes.
Yeah.
Okay.
So sets together with such two argument relations form a category.
Yes.
And then, in fact, it's even a two category because F and G being subsets, they can be related with some other subsets. So among these subsets, you can allow inclusions. And sets together with relations and inclusions of these relations form a two category. Okay. And then in this category, if you even forget about these inclusions, in this category, this one category, you can speak about the group object. So what is the group object? Gamma or G, whatever, is called the group object if you have a relation from G to G, G cross G to G, okay? It's called multiplication. You have the unit which goes from the singleton to G, and you have the inverse from G to G, and all they are relations. However, one of the axiom of the inverse is that it is an involution. And it is known that every invertible relation must be a map. So you can assume that S is simply an involution in the sense of a map. Okay? And then if you assume usual axioms for this structure, you obtain something that's called a group object in this category. So the theorem of Zakrzewski is that this group object, it's a datum is equivalent to a groupoid when the image of this singleton under this relation, which makes it a subset of G, becomes the space of units. These are units. Okay, and all actions of a groupoid could be gotten from this. Okay. Such objects can be. Where is the next page? This one? No. Maybe this. It doesn't work. I cannot open the next page. It's strange.
Anyway, the time is up, so maybe.
Okay.
Just
So you know what does it mean to have a groupoid homomorphism in this sense. It is again some relation, okay, which is compatible with this structure.
Okay.
And again, there's a theorem that if you have these groupoids, to every groupoid you can with a groupoid you can associate a sister algebra, and morphism of such groupoids in the sense of this Zakrzewski relation will induce you a star homomorphism between these associated sister algebras.
Okay.
So in a nutshell, it's all about Zakrzewski morphism.
Okay, so yeah, thank you very much. So it's time to wind it up. I stop recording.